Trivia. Now, if you guys could all turn in your sheets and your pencils, and the pencils, to Sam, who's over here. Sam, wave. That would be great. We'll grade them during the first talk, and then we will announce the winners after the first talk. So now we're going to switch the slides, and then I will introduce the first speaker.
Yeah, what do I need to do? Like, I have it, but I don't know how you turn it on or anything.
Yeah, we'll meet.
Okay, you've got the power.
Hi, Sydney. Turning in your trivia sheets. Now I'm going to introduce the first speaker. Tonight we have Tom Wagg, who's going to be talking about gravitational wave sources in our galactic backyard. Tom is a second-year grad student at the University of Washington's Astronomy Department and my office mate. And that is his biggest accomplishment. Thank you for recognizing that. Without further embarrassing Tom, here's Tom.
Hey guys. Okay. I'm gonna probably move around, so okay. About that close? Cool. Okay, hey guys. Hey. My name's Tom. I have not given one of these before, so go easy on me. But yeah, what we're gonna be talking about today is gravitational waves, and specifically the ones that are residing in our galactic backyard. And this is basically to do with a paper that I've written over the past year or so, and I'll show you some of the results. We'll talk about some of the background. It's going to be fun. Background on me, if you're from the US and you think I sound strange, it's because I'm from England. If you're from England and you think I sound strange, it's because I've lived in the US for like 6 years, and so now I have a strange accent. So, let's just do some quick facts real quick. So gravitational waves, they're pretty new. We basically found the first gravitational waves in 2015, not that long ago. And since then, we've kind of been racking up the numbers, and we've now found about 90 confirmed gravitational wave sources. But all of those are really, really far away. We have found 0 sources within our own Milky Way. We have found no sources in our galactic backyard. Crazy, right? And so now I'm going to tell you how we can do that. So let's just do a brief outline of what I'm going to go through. So first we're going to start off, we're just going to do some background. We're just going to go, what are gravitational waves? How do we detect them? Why should you care about them? I'm going to really motivate all of you. You're going to love them as much as me. And then we're going to start talking about the LISA detector specifically. And this is like, why do you send a detector into space? What are the advantages we're going to gain from that? And once you've kind of worked out how the detector's working, you've got the background knowledge, we're going to start talking about the results that I've got specifically for you, which are really more about these local sources. What are we going to find within our galactic backyard? And then finally, we'll just wrap up. I'll tell you a bit about a Python package called legwork, and you'll get ready for Tyler's talk. So, let's do this. First, we're going to talk about background. We'll talk about gravitational waves. So, if you kind of could take a look out far deep in space, and you looked at some dramatic, massive binary with 2 black holes and saw them spinning around, and you really exaggerated the effect, this is what space-time would look like near there. What you see is any orbiting pair of masses is going to emit gravitational waves, and these are going to ripple through space-time. And this doesn't need to be something supermassive. You could stand with your friend, hold hands, and kind of spin around in a circle, and you would emit gravitational waves. They would be very weak, unless you are particularly massive. And so we don't often detect these. But the kind of effects that we have from this is those waves are going to stretch and squash space-time itself. And so that's going to change distances, which is going to be very key for how we can detect them. So they're going to go through space, and they're just going to stretch it, and then squash it, and slightly change the distances between objects. So if we kind of looked at the Earth as gravitational waves are coming through it, you can see it start to kind of oscillate and stretch and squash as the gravitational waves go through. This is, of course, vastly exaggerated. That would be problematic if we were standing on Earth. Luckily, it doesn't work quite like this. But, you might think to yourself, okay, this is happening all the time. Like, any sort of massive binary is releasing these gravitational waves. Why did it take till 2015 for us to properly detect them? Well, I mean, for the majority of masses, as I've said, that it's immeasurably weak. It's similar to how I'm standing in front of you, and you are gravitationally attracted to me, but you're not all flying towards me because it's extremely weak. In reality, what you need, if you really want to detect these, are some sort of compact object. And by that, I mean something like a black hole or a neutron star. And these can end up creating nice, strong signals for us to detect. And the moment at which this signal is strongest is when the separation is smallest, and so it's when they merge. These things have been spinning around each other, they get closer and closer, they smash into each other, and they release this huge burst of gravitational waves. And that is what LIGO and ground-based detectors tend to detect. So, let's just talk a bit more about the sources that we're looking at, these compact objects, these binaries. If you haven't heard of a binary before, a binary system is just a system where you've got two objects, two stars, maybe two black holes that are orbiting one another. And so maybe if you're thinking about Star Wars, if you look at Tatooine and you see two suns in the sky, that is because it's a binary star that the planet is orbiting. And what you should know is this is actually very common for massive binaries. So massive binaries, things that are going to tend to produce these black holes and neutron stars that we detect, are actually most of the time formed in a binary. Once you're above like 7 times the mass of the sun, pretty much everything is formed in pairs. It's not like the sun that's all alone. That tends to just happen with the lower mass stars. But still about half of them. Binaries are important. And so the things that we're actually detecting are compact objects, and these tends to be the remnants or like remains of a dead star. You've had a star that has evolved over time, it's gone supernova, and it's left something behind. Maybe it's a black hole, maybe it's a neutron star, something like that. And so the nice thing about this is gravitational waves are going to give us a direct insight into the evolution of massive stars, because they've got to evolve, turn into something, and then we detect what's left behind. So we can learn about stars by looking at gravitational waves. And some of the typical ones that I'm going to focus on today are kind of like a small subset. We're not talking about all of the possible sources. You can have like supermassive black hole binaries where something's falling into the like huge black hole at the center of the galaxy. You can have like primordial black holes from the origin of the universe. We're not going to talk about that because it all gets complicated and you have to do general relativity. So I'm going to make it easier, which is the reason I did my research on this bit, looking at stellar origin binaries. So these are ones that are formed from stars, and they lead to sort of massive compact objects. And basically, you're going to have 3 types. One, you've got a binary neutron star. I'm going to just call them like NSNS. So those are 2 neutron stars orbiting one another. Then you can have a black hole neutron star binary, where you've got one of each of a black hole and a neutron star orbiting each other. You can probably guess where this is going. You then end up with a binary black hole. And those are the most massive and often the strongest signals. So we tend to kind of see most of the ones on the right and then fewer of the ones on the left. So those are our sources. We know what gravitational waves are. So now, how do we detect them? So this is a picture of one of the LIGO sites. And this is how a ground-based gravitational wave detector works. Because if you imagine, it's kind of difficult. You're trying to measure some change in distance, but it's not like you can just put a ruler down, because your ruler is also going to change in size. It is difficult when the entirety of space-time is stretching and squashing. But scientists are clever. And what you can do is basically fire some lasers out down these like long pipes. And hand waving a bit, they do something called interferometry. But what they essentially do is time how long it takes the laser to cover a known distance. So you know a laser is going to move at the speed of light. That's fixed. You know how far the distance usually is. And so if you can measure a change in how long it takes that laser to come back to you, you're also measuring how much the space has stretched or squashed. And so you can then measure the strength of the gravitational waves and where they come from and things like that. And so that's basically how a gravitational wave detector works in a very hand-wavy way. But the nice thing is that we don't just have one of these. They're all sorts. So if you notice, the LIGO Hanford site is actually really near here. It's in eastern Washington. Recommend visiting if you can. I still haven't, and I want to. Where exactly? I don't know. David, where is it?
That's Hanford, close to Tri-Cities.
Close to Tri-City. There you go. So there's a bunch. You can see there's several LIGO detectors. There's also Virgo. There's Cagra. For reference, if you hear me say LVK at any point, I'm just talking about the collaboration of ground-based detectors. But the nice thing is if you have them in lots of different locations, you can imagine like the way that GPS works, if you want like triangulation of different satellites. Similarly, if you have different gravitational wave observatories, and they'll measure this stretching and squashing at slightly different times because the wave has to pass through us, and you can use that to kind of localize on the sky where it came from. And so you can pinpoint where exactly did that gravitational wave come from, which is fun. Because it's not like a regular telescope. You don't like point it at a point in the sky and you're like, I want to look there. You're just constantly looking everywhere. So that's how you kind of narrow down where you're looking. And then the last bit of background I want to do is basically the why should you care? What can we learn from gravitational waves that we can really add to what we know? And I think the immediate obvious answer is this binary stellar evolution. You're going to have stars evolve in some way, result in these black holes and neutron stars, and you can learn about how this works. Maybe you can constrain it in some way. And I'm going to show you some ways that we're going to do this specifically. But you can also learn about the formation mechanisms of these compact objects. Like, do they all start off in binaries? Do they start off apart and they kind of end up together or things like that? Which is kind of very interesting for the dynamical situation going on in the galaxy. You can also learn about the structure of neutron stars. If you go to the University of Washington, talk to most people in the physics department, like odds are you'll pick someone who's talking and thinking about the neutron star equation of state and the structure of neutron stars. And this is a great way to look at it. If you have a merger of a gravitational wave event, you can then kind of deduce what was the structure of that neutron star, what's going on inside it. And the nice thing about neutron stars as well is they also enrich the universe. So lots of the kind of gold and platinum and things like that, you get out of supernova, but you can also get it out of the merger of a binary neutron star. And so this is how you're enriching most of the universe with these heavy metals that you couldn't have got otherwise. So if we can measure how many of these gravitational wave events are there, maybe we can measure how often we are enriching the universe in this way. And then the last thing is that you can then test general relativity in very extreme conditions. So we think Einstein's right in the same way that we thought Newton was right. And so what we want to do is really make sure that general relativity does accurately describe gravity, even around the closest interaction between two black holes. And this is a great way to test that. So with all of these things, you can learn things just using gravitational waves. So hopefully you're now also as excited as me about this way of viewing the universe. And that's all of your kind of background. And now I want to talk a bit more about the LISA detector specifically. So this is going to be a whole new realm of the gravitational waves. So LISA looks like this, or it will look like this. It is a planned space-based gravitational wave detector that's basically going to follow the Earth in its orbit. You can see it's got like 3 satellites kind of tumbling around. That tumbling helps give you sky position. That's why they do that. And they fire lasers between each other. And they basically work the same way as LIGO does, except with some redundancy by having 2 sets of arms working together. And this is planned, hopefully, to go up in 2034. If it's anything like James Webb, it's going to be much later than that. We'll see. But I hope it does. And what you can immediately know is that it is physically much larger than LIGO or any sort of ground-based system. You can see this is way bigger than the Earth. And that's going to be important. So at this point, you're like, okay, so it's basically LIGO, but we've put it in space. No, do not think that. What I want to emphasize is that it really has some unique advantages. We've already got LIGO, sure. But if we look at what LIGO is sensitive to, it's a very specific area on, well, this plot. So what we're looking at on the y-axis here is how strong are the gravitational waves. Basically, if you end up inside this bucket, you can be detected. If you're below it, you can't. And what you see on the x-axis is kind of this frequency. So things on the right-hand side are close to merging. What I said was LIGO really looks at things as they are about to merge. But if you're still far apart, if you're on the left-hand side of this, LIGO basically can't see. Like, you've got all of these sorts of things, and LIGO, sure, it's great for these red ones, But any of these on the left, like the extreme mass ratio inspirals, any of the galactic sources, it really just isn't sensitive to. But the nice thing is, LISA will be. So the LISA sensitivity curve lies here, and it can see all of these wonderful things. And that's why LISA is going to be important. So let's just do a quick comparison between what a space-based detector is and what a ground-based detector is. So for example, we've got LISA and LIGO. They could be two examples of this. So as I've just said, the frequency range is different. You're looking at lower frequency things for LISA than you are for LIGO. What I just want to emphasize here as well, that's hertz. So that's like once per second. So it's on the order of that. And that's pretty much equivalent to the orbital frequency of these things. So you've got two black holes going around each other. And they are basically orbiting once per second. So it's like us going around the sun. Instead of doing it in a year, we do it in 1 second. And we're like two black holes. Like, it's insane situations. But we're going to look slightly at lower frequencies of LISA. And this is important because what you see is instead of looking at that merger, you look at the inspiral. These things are still kind of slowly going towards each other. Maybe they're a bit sluggish at this point, feeling lazy. They haven't quite smacked into each other. But LISA can still see them. It doesn't require for them to, implode, which is nice. And this has some advantages. So one maybe thing that looks like a disadvantage at first is that there is now a limit on the distance. So LIGO can see things like billions of light years away because the merger is where those strong gravitational waves come in. But if you want to look at the inspiral, they're kind of weaker, and you can only really detect things in nearby galaxies. And honestly, for the most part, basically just the Milky Way. And that sounds like it's annoying, but it's actually kind of great for the theorist in me because I don't have to model the star formation history of the whole universe. I just have to do it for the Milky Way. And so this kind of helps constrain things a bit. I can fix certain things, and then only other ones need to change. So that's nice. And the last thing I just want to mention here is eccentricity, which is something that basically doesn't happen in LIGO. So eccentricity is a measure of how circular is the orbit. If you've got 0 eccentricity, you're just going around in a circle. But as it gets closer and closer to 1, you basically stretch out, and you go around in these long loops that are just kind of slow and then fast around the corner. In a corner if you have a corner in a circle. But essentially, LISA can detect things while they are still eccentric. By the time you get to LIGO and you're close to merging, you'll have gone into a circle. But you can detect the eccentricity if you look at them a bit further back. And this is nice because it's basically an extra parameter, like something that you couldn't possibly know. It's been erased by the time you get to LIGO. And so this can help constrain lots of things about our sources. So space-based detectors are very cool. And so now I want to just kind of go through how sensitive LISA is because it's kind of insane. So you got this thing out in space, it's firing some lasers around. Each of these arms are 5 million kilometers in length. So if you take that and you kind of, in equivalent, if you went 125 times around the center of the Earth, you would get that distance. So that is the distance that it is in full. And it now needs to measure changes in distance. But these changes are still incredibly small, even given the size of the strength of these gravitational waves. But LISA is able to measure shifts in separation down to the width of a human hair. It's 5 million kilometers in length, and it can measure a change in separation down to a micrometer. It's incredible. And then, okay, let's put this another way. Say we come down to Earth, we're down on Lake Superior, and we're like, oh, this lake's nice. This water's looking lovely. I want to take some of this home, show my friends. I pull out my water bottle, and I take a liter of water out of Lake Superior. That's going to change its depth a bit, right? Probably wouldn't notice that. LISA will notice it. LISA can measure that change in depth just by taking a liter out of the lake. It's absurd. This is a very, very cool detector. A lot of respect for the engineers. I have no idea how it works. Super cool. So the nice thing is, LISA is also, it's a very collaborative instrument. It's very happy to team up with other people. And so there's two types of ways that it kind of teams up. First of all, it teams up with LVK. Remember, this is those ground-based detectors, that collaboration. This is sometimes called multi-band detections if you're kind of into it. But basically, you've got systems that are going through their slow inspiral in LISA, but one day they are going to merge. So what LISA can do is basically go, oh, guys, guess what? There's a merger coming in exactly 10.73 years. Get ready. And so they can kind of work together in this way. And basically, you've got all the ground-based detectors, and they're just kind of looking over your shoulder and like, oh, yeah, I see what you measured. I feel like I could constrain that as well. And so you've got this warning happening. But it's also kind of nice because the two instruments have different advantages, right? I've told you that LISA is going to measure all sorts of frequencies and eccentricities really well. But what it doesn't measure that well is the individual masses. It knows how massive the thing is in total, but getting the individual ones is hard. But LVK can do that really well. So if you measure it with both, then suddenly you're like, boom, okay, profit. I've got a great source now. It is extremely well constrained. So that's like one way that you can really kind of get a collaborative effort going. Another way is, okay, we've got something measured with gravitational waves. What if we measured it with a telescope as well? What if we have some sort of electromagnetic detection? So this can happen in different ways. If you've got a merger like in LIGO, then you can get all sorts of like explosions and kilonovae. These don't really happen in LISA. What we focus on for our kind of main electromagnetic counterpart are pulsars. And I just want to briefly like just completely go off on a whole tangent because I want to tell you how pulsars were discovered because it's super cool. And it lets me tell you about a super cool person. So just as a brief aside, this is Jocelyn Bell Burnell. And basically she was a grad student, I think it was like 1967. And she was looking through this radio data and she saw this repeating radio source. And it was really weird. She thought it was like some sort of problem with the detector that she just built. And eventually kind of went over it for several months and was like, this must be real. She took it to her supervisor, and her supervisor was like, no. And for reference, she also called it LGM1, which stands for Little Green Man 1, because she thought it was extraterrestrial in origin. But basically, she then found a second source, like 2 months later, and her supervisor was like, oh, okay, I guess you're right. And then this is the annoying part of the story. We then fast forward 7 years, and her supervisor gets awarded the Nobel Prize, and she gets nothing. Indeed. Yeah, I mean, 1970s, people are awful. But this has a reasonably nice ending in that now Dame Jocelyn Bell Burnell is a renowned astrophysicist, professor at multiple institutions. Everyone loves her. So I actually met her like 2 years ago. She's wonderful. She came and gave like a public talk and then had a lecture with us. Like she's very enthusiastic about getting people into science. She got given like $2.3 million like to kind of sort of make up for the Nobel Prize, and she just immediately donated it to like helping get underrepresented minorities, women into astrophysics. She's awesome. Yeah. So yeah, you should know this name. Anyway, aside of going back to kind of multi-messenger detections. Okay, so we've got these pulsars, which Jocelyn discovered, and the nice thing is that we can basically use this to better constrain in the same way. So the kind of, if you measure them with radio, you can measure the frequency really well, but then you measure them with LISA and you get the mass as well and things like that. And we can learn things like how many neutron star binaries tend to contain pulsars, because we'll be able to get all of them with the gravitational waves, and some fraction of them will have pulsars in them. And we can maybe increase the sample size that we use for pulsar timing arrays. There's lots of cool things we can do with pulsars. I can talk more about this if you want, but suffice to say, LISA is also very collaborative. And so now I have told you about gravitational waves. I've told you how we detect them. I've told you why to care. And we've also talked about what LISA is. So now I want to tell you about my research specifically that I've been doing over the past couple of years on focusing on our galactic backyard. So these gravitational waves, they're a little closer to home. And let's talk about how we make these predictions. It's basically a three-step process. First, we're going to need a bunch of binaries. We're going to need those kind of binary black holes, binary neutron stars. So we need to make a population of those. That's one thing we need to do. The other thing we need to do is build the entirety of the Milky Way and simulate the whole thing. Easy. So what we need to do is come up with some model for that. That'll be step 2. And then step 3 is we need to actually perform the evolution. So they're going to start in some place, and they're going to start with some separation, but they're going to shrink over time and move. We need to account for that. So that's going to be step 3. So let's just go through each of these a bit more detail. First, we need to make the binaries. So the nice thing is we have a good understanding of kind of the rate at which stars form, and maybe distributions of what the primary masses should be, and the mass ratio, and how separated they should be. We don't necessarily know what they will turn into. The hard part is then we have to evolve those stars, right? We need to say, okay, how do they die? What do they become? Do we get a black hole? Do we get a neutron star? And so which one of those end up becoming our gravitational wave sources is the hard part. We start off with this kind of stellar binary. We need to throw it into some black box and then find out whether we get something, I don't know, maybe like a black hole neutron star binary. Luckily, this black box exists, and it's called COMPASS. So this is, it's known as a rapid population synthesis code. But essentially what it does is takes all of these starting binaries, evolves them into whatever they end up as. Maybe they just end up as stars. They haven't evolved long enough. Or maybe they end up as a binary black hole that can be detected by LISA. And so using COMPASS, we can then fully evolve all these stars and get a nice population. Step 1's complete. Great. Step 2, we need to build the whole galaxy, as I said, easily done. The trick is just to completely overly simplify everything and just say, oh, it's just made of 3 components. So say we take another galaxy. We look at like this NGC 4565, sometimes called the flying saucer galaxy. If you look at it, you can kind of see it's kind of made of a few different parts. Like it's got this kind of like bulgy bit in the middle. It's got like a thin kind of dark disk, and then it's got this diffuse thicker one. Great, those are going to be our 3 components. We're gonna basically go, okay, great. I've got a low alpha, which is just like the thin disk. I've got a thick disk, and I've got a bulge in the middle. Cool. Basically, that gives you all the positions. And then, okay, it's a little more complicated than this. I have oversimplified it. But each of them produce stars at different rates. They have different kind of metal abundances, and you have to account for where they are and how they're moving. So I'm kind of waving my hands a bit here, but suffice to say, we did simulate the whole of the Milky Way, and we got all of these binaries, and we put them at realistic positions and at realistic times. Great. And then we just need step 3. We need to know what they are at present day, because that's what actually matters for what we can measure. So what's going to happen over time is that binary is going to shrink. It's spiraling in towards each other, releasing those gravitational waves. That's releasing energy. That energy has to come from somewhere, and that somewhere's the orbit. So as it spirals in, it gets closer and closer and closer together, and then eventually merges. And so because of this, we need to know, okay, how has the binary evolved? At what stage is it at now? And what we kind of need, what we're looking for, is something with a small separation. So we're basically in a bit of a Goldilocks situation here, where, I mean, we could be a bit too early. Say we come too early, the thing's really far apart, they haven't got strong gravitational waves, you can't detect it. Say you get there too late, the thing has already merged. At that point, you're like, okay, it's not emitting gravitational waves anymore. It's not a pair of objects, it's just a single one. So because of that, you can't measure it. But you can get it just right. So a small fraction of these black hole binaries and other binaries get close enough that they're emitting gravitational waves that are strong enough to be detected at present day. And so basically, we kind of integrate the orbits, we kind of check where they move in the galaxy, we move them closer, and we get some population of things. And at that point, I can show you some results. So, big reveal. Basically, what we estimate is, I don't know what happened there, but that 1 should be up there. But this is how many we predict. What we estimate for a 4-year LISA mission, which is the default, we estimate we're going to see about 120 of these objects. They're going to be kind of distributed like this. We're going to see mostly binary black holes, some black hole neutron stars, and then just a couple of binary neutron stars. And if you extended this to 10 years, which is something that they're considering doing, you'd get like 200. So, you know, okay, cool. That's how many we're going to detect. That's not necessarily the interesting part. What we want to know is, what sorts of things are we going to detect? And so now we've got a whole plot. Don't worry, we're not going through this whole thing. There's a lot going on here. What I'm going to do is just zoom in on one of the panels first. What we're going to focus on in this part of the plot. So what I'm showing you here is a distribution of the primary black hole mass. So on the left here, we've got low mass things. This is only like 2.5 times the mass of the sun. On the right here, it's like 20 times the mass of the sun. So they're getting quite big at that point. Y-axis is just like some normalization. So what you see is the distribution. And so this purple curve showing you where the binary black holes are. The pink curve showing you where the black hole neutron stars are. You'll notice that the double neutron stars are missing. Those don't have a black hole in them, so they're not on the plot. So what do we see here? Well, first of all, we're not biased towards kind of higher mass things. If you look at LIGO detections, if you're familiar with them, they're going to detect things like 30 solar masses and like higher, because they're really biased towards the heavy things, because the heavy things are louder, so they're the ones that you're most likely to detect. LISA doesn't have that bias. LISA's like, I'll see the whole galaxy equally. Like, I'm happy to look at these low mass things. So this is one thing that you should immediately notice is we're seeing a more intrinsic distribution of what the black hole mass distribution should look like. And then the other important thing to take away from this is there is a significant fraction of things hanging out in the lower mass gap. So this lower mass gap is an observed mass gap. So we haven't really found many black holes between like 2.5 and 5 times the mass of the sun. And we're not really sure why. there's a debate over whether it is a physical thing, like for some reason things don't form there, or maybe we've just got unlucky and we haven't seen one. But what we show here is that we're actually predicting we'll detect a lot of things within that lower mass gap. We're predicting it exists, and we'll be able to prove whether it does with LISA. Because with LISA, you can then say, okay, I've detected things in this gap. Great, it doesn't exist. And so that's kind of the masses. I want to show you one more panel from this plot. So if we just zoom back out, what I want to focus on is this one down here. I want to look at the eccentricity. So remember, this is telling you how circular the binaries are. So on the left, this is a log scale, but on the left, basically what you've got are circular systems. These things are pretty much an entire circle. These things on the right are extremely eccentric. They're basically like a straight line. They're just like whizzing back and forth. And that's where it gets really fun. But I'm going to just divide this into like 3 sections. You've got like this bit on the left that are effectively circular, pretty boring. I don't care about those ones. Then you've got like this mildly eccentric region where you can measure the fact that it's eccentric, but again, I do not care because it doesn't really affect things very much. What I really like is this highly eccentric region. Once you get past 0.3, cool things start happening. Like you start seeing some really dynamical effects where the eccentricity is affecting the orbit, and it implies that something really cool has happened in the past. It's had some sort of huge supernova which has kicked it onto this crazy orbit, and so you can learn lots of stuff about those ones. So first of all, only like a quarter of them are boring and effectively circular. There's a lot going on with these more eccentric ones, and in particular, we find that about 16% of them are in this highly eccentric region. So we're going to find a bunch of things that are highly eccentric, and using that we can learn about how supernova work and how strong the kicks are, and all sorts of cool things. So eccentricity is going to be really interesting from LISA because we're not going to see it at all from LIGO. So that's something that I really want you to kind of take away from this. And this is the last plot I'm going to show you, the last result I've got for you. Now we can talk about how we can use them to learn about stars. So what I'm going to show you is a detection rate. What you can see on the y-axis is how many things you detect in a 4-year mission. So at the bottom, you're only detecting like one thing. On the top, you're detecting like 500. So there's a large range that I'm showing you here. And the right-hand side y-axis, it's not too important, but that's what it is if it's a 10-year mission. And over here, I've got a bunch of models. So I've got like models A through T, 10 different models of what happens if I change the way that stellar physics works. Because there's lots of things that we don't know that it works a certain way, so there's lots of kind of options that I can just basically toggle. And these are all the options, which I'm not going to read out, but I'm just going to summarize. So what we've basically got are mass transfer. So say you've got 2 stars that are near each other. They're going to start kind of transferring mass, going through each other. How efficient is that? How stable is it? How fast does it happen? Those are the sorts of things we're varying. Common envelope. If you get 2 stars that end up close together, you can basically get in this situation where you have 2 cores and then a big diffuse envelope around both of them. And that is something that, like, if you saw the modeling for this, you'd be horrified. Like, we do not know how this works. But, you know, that's a great bit to focus on because then we can get detections and we can constrain it. So that's why we vary a lot of things in that. Another thing that we want a bit more information about, supernova. How strong are they? How big can a neutron star be at? Should black holes be kicked by supernova? All sorts of things like that. That's what's getting varied in supernova. And then the last one there, just a little dinky small one, is the stellar winds. So you've maybe seen like the sun has like a solar flare every now and then, things like this. With massive stars, this can kind of happen constantly. And if you vary how much it happens, you're going to lose lots of mass, and that's going to affect your black holes. Blah, blah, blah. You get gravitational wave sources that are different. So if I kind of move those labels out of the way, what we can do is add the real data. And so this is what we see. So you see there's a huge variation, which is awesome. So this kind of gray one that's going across, that's our default model, and you can kind of compare the other ones to it. But you can use this in, okay, let's say LISA detects like 90 things in a 4-year mission. So what you can say from this is like, okay, well, it looks like that model looks pretty good. But these ones are pretty close, so maybe they're right. But these ones down here, you're like, that's not how physics works. That clearly is not right. And so you can then just kind of rule out that model for stellar physics. You can say, okay, mass transfer does not have an efficiency of 0.75. It just doesn't work that way. And so you're looking at, you are then kind of learning about the way that stars are evolving and how they interact by looking at the LISA detector. And we're looking at the remnants of these dead stars, and we're learning about the lives that they led just by looking at basically their carcasses. And so I would argue we are basically archaeologists because we are digging up the remains of stars and we are learning more about them. And those are all the results I have for you. So now we're just going to wrap up. I'm going to mention legwork briefly, and I'm going to release you to Tyler. So, takeaway messages, things I want you to remember from this talk. First thing I want you to remember, think about gravitational waves. They are things that stretch and squash space just a little bit. And they're a new lens that we can use to look at the universe. We don't need a telescope that needs photons now. Now we can just use gravitational waves. It's a whole new way of looking at things. I want you to remember the LISA detector, and that it measures the in-spiral instead of the merger. We're looking at it early on in its evolution, and that lets us learn about a different population than ground-based detectors. And then finally, I want you to remember my research, of course, most important. I want you to remember, we're predicting LISA's going to detect, hundreds of massive stellar origin binaries, and we might be able to use them to constrain stellar evolution, depending on how many we detect. Maybe we can rule some models out. And I just wanted to mention this briefly for any coders or software engineers in the audience who like doing this sort of thing. Say you want to try making these predictions yourself. You want to kind of test out how LISA works, how strong gravitational waves are. So Katie and Katie is a postdoc, and she's going to be a professor now at, where is it, Carnegie Mellon. And we made this Python package called legwork, which is the LISA evolution and gravitational wave orbit kit. We definitely came up with the acronym first. And so this lets you evolve those sources like I was saying. It can calculate a gravitational wave strain, which is like the strength, signal to noise ratio. It can work out what the sensitivity curves are for different instruments, and then it can visualize all the results. So if you want to try this at home and you like Python, you can maybe learn a bit more about the detector. You can read the docs. It's legwork.readthedocs.io. Yeah, and that's about it. So there are my takeaways. Thanks for listening. If you want to see the paper in like a more casual way than reading a full paper, I have like a blog post type thing here with like a layman's summary. Yeah, that's it. Thanks for listening, guys. That was fun. Oh, right, yeah. And I should also ask you for questions. Anyone got questions? Yeah.
I trust that gravitational waves are subject to interference patterns like other waves. How does that complicate detecting sources of them?
Yeah, okay, so the question's about kind of interference with gravitational waves and whether that also affects them, and yes, it's rather complex. What you end up having to do is you basically produce waveforms of what you expect, and then you have to do match filtered analysis on all of the signals. So you have a series of things that it could be, and you have to pull them out. And so this isn't that bad with LIGO, where you get like one huge signal, right? With LISA, it's gonna be a whole hassle to do, because you turn it on and you see everything at the same time. And so the way it's gonna work is you're gonna pull them out one at a time. Basically, you'll find something that's very loud, you'll take that out, the noise level will reduce. You'll find something else, you'll take that out, noise level will reduce, and you can kind of reduce the interference in that way by taking the strongest thing first. Yeah. Other questions? Yeah?
Would you be able to go to the slide of like the differences between LIGO and LISA?
Yes. Take me a second. I have too many animations. It's definitely a problem. We're getting there. This is a great recap. And hey, Jocelyn, cool, stuff moving. Yeah, you forgot about that, didn't you? Yeah. There it is. This is what you meant, right?
So for phase detected, what I'm kind of getting from this is that LISA doesn't detect the merger,
Yes.
but the merger creates like the biggest gravity wave.
Okay. This is confusing, right? Because you'd think, okay, mergers are going to be the strongest gravitational waves. Why doesn't LISA detect all of those? They're rare. It's not that it won't detect them. It would detect them if they happened, or like if they happen in the right frequency, so they have to be very massive. But for stellar origin binaries, the merger happens at a certain frequency range, so mostly isn't visible to LISA. LISA can see the more massive ones, but they're just kind of rare. So if they do happen, it's possible it'll see a couple of them, but it's far more common that the things are going to be far apart, because the merger happens on the time scale of like a couple days over a couple millions of years. So just the population's very small. Yeah, of course. Other questions? Yeah.
So like with the telescope, there is you have to aim the scope at the thing. Is there a directionality between the detector and the origin of it?
Gotcha. Yeah. Okay. So the question is, basically, can you point a gravitational wave detector at a certain point, if I can summarize? And you don't need to, essentially. So with the ground-based detectors, you have lots of different ones. And they are all looking in all directions at the same time, but the difference in timing means that you can then work out roughly where it came from, basically by a sort of triangulation. Works differently for LISA, but if you remember, it's in a triangle, and you know LIGO is in like a cross shape. That triangle is basically two of those cross shapes covered up. So you have two to kind of do different timings, and at the same time, if you remember the way it was orbiting, it's kind of, maybe it's actually just very close. How do I make the video play again? Yeah, so the way it's moving, you see it's kind of tumbling, it's not always at the same angle. That means that as it goes around, remember these gravitational wave signals are like, they're not like at a moment, they're going to happen over the whole 4 years. So you can detect it here, and then there, and then there, and you'll be at a slightly different angle. And that basically lets you narrow down where the position is through some like complex geometry stuff. Yeah?
So along the same lines, you said in order to like detect gravitational waves, you need a certain accuracy of the distance between these things.
Mhm.
How is that accuracy like not subject, or I guess how do you compensate for like the distances or differences in gravity to satellites, like the differences in time scales of each of those that's subject to different gravity?
Yeah, it's hard. So kind of like what you're asking is essentially like disentangling different sources, how they all have different separations and slightly different strengths, and how can you find the differences? Is that basically it? Yeah. So it's hard, and it's kind of in relation to this question of you take the easy ones first. So there are some that you're never going to be able to resolve. It's like if you had it in terms of sound, it's just like this low humming that you never hear, whereas these other ones are like screaming at you. And so you deal with the screaming child first and then get to the humming. So you get to this very loud one first and you kind of pull that out. And that one's easy. You can say that, okay, that one's got to be very close. And then as time goes on, you can kind of start pulling them out like that. But yeah, it's going to be hard. There's a lot done on this. So obviously this isn't going up till 2034. They're not entirely ready. They've got a lot of the infrastructure in place for circular binaries. One of the main points I was making in my paper was like, only 25% of them are circular. You guys need to have models and waveforms ready for eccentric sources. They start having harmonics, and it's like, instead of a single person, it's like a whole choir of things. It gets crazy. Yeah. Yeah.
On your slide where you had your models A through T.
Yep.
And then you had like Lisa would detect, say, 90 events, and you ruled out some that were out of this one.
Yeah.
How were you able to rule those out, or why could they not just be like rare enough that you wouldn't see them in the Lisa time frame? What's the difference between ruling a rare event out?
Yes. Great question. So on that plot, if you'll, well, I will go there as I talk. But on that plot, there are a series of dots, but also with uncertainties, right? And so what I did was I didn't just make the Milky Way once. I made the Milky Way like 250,000 times and then sampled from it. And what that gives you is uncertainties. And so you have those like, the lines are 1 and 2 sigma uncertainties. And so that is basically, if you have a random thing and you get unlucky, like you're saying, then you could end up at the bottom of that range. And sure, it is possible that you could end up like really down here, but this is 2 sigma, like that's like 95% you're going to be in that range. Or 95% you're going to get that high. The odds of you getting up to that 90, it's just not going to happen. As long as we understand the modeling of the galaxy correctly and the modeling of stellar evolution correctly, which is a big if, but given those constraints, that's why. Does that answer your question? Go. Okay, one more? Yeah? Wait, Connor. Look out of here, I'm sorry. Wait, does anyone else here? I do not know what that means. You know more than me, I'm sorry. Yeah, cool. Okay, thanks guys.
Switching. Yeah. How do I do it? Okay, there we go.
I'm just going to jump in really quick. Thank you all for coming out tonight. I'm Frank Castro. I'm the owner of Bickersons, so thank you for coming out.
Oh, I gave it to
My wife, Sean,
Megan
the other
wants to.
owner's inside. But I know she's going to go over quiz stuff right now. But before the next speaker starts, we'll do last call and give everyone a chance to come out and get another drink before you come out. Thanks for coming out tonight. Thank you.
Thanks, Frank. So now we're going to do trivia answers, and I'm also going to announce the winners of the trivia, and then we'll move on to the next talk. So answers first. Let's get started. It takes the moon every 27.3 days to orbit the Earth, so about a month. In 1609, Galileo was the first astronomer to describe the moon's surface as being mountainous. Buzz Aldrin's first words were "beautiful view" after stepping on the moon. The moon reflects less than 15% of the sunlight that hits it. The First Men in the Moon is a scientific romance novel by H.G. Wells. Gravitational waves are invisible ripples in space-time, which you should all be experts on by now. Albert Einstein predicted the existence of these waves in 1916. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. LIGO directly confirmed the existence of gravitational waves by observing a black hole merger. And finally, it is true that LIGO can convert the signal into a sound. Okay, now on to the winners. So, we have 2 people that got 8 answers right, and they are the runners-up, and 1 person that got 9 answers right, and they are the most ultimate winner. But everybody gets prizes. So what I'm going to ask is that you wait until the end of the second talk to come get your prize. But the first 8 answer person is Gray, Ohio. Gray, Ohio. That's clap. Okay. The next 8 answer winner is Chillin' Krillin. Well done. Okay, and the ultimate winner of the night that still got 1 answer wrong, so. I'm just kidding. I'm just kidding. That is ICU2. Yeah. Okay, well done, you guys. So, with that, we are going to take a brief 5 to 10 minute intermission so everybody can go do last call if they want, and then we are going to get started with Tyler Gordon on how the moon formed. Hold on, let me switch these real quick. Grab a black holes.
I'm gonna try to do this again.
Do you need help?
I don't think so. I think I was using like the bad port on the.
Oh no.
That, so unlucky.
Wait. Can I see the speed? Did you do the Tom quote that was,
The corners in the circle?
I was thinking, so I don't care about that.
Sorry, we got so many of your great quotes, Tom.
Oh, really?
Yeah, great quotes from Tom.
What they put on Twitter was like, don't take water out of like Michigan diesel.
I'm so proud of you. Tom, that was really good. Well done. Cheers.
Jackie's doing live stream.
Bring my charger. I thought I packed it, but you can just leave this if you wanted.
The Tom tweets are going viral. Tom tweets are going
I
viral.
thought it was on 50, so it should be fine, but I just wanted to
Oh, you're good, you're good, you're good.
Hey Megan, that was right in front of the camera.
It's not a script, it's whatever comes to mind.
So you're
Oh, Tom, he's right there. I was hoping you were
When it crumbled, I got the what's the velocity of a gravity wave moving at speed light? Speed light. Oh, you know that?
I feel like they
What if it's a spinning Well, it's the weird thing is like this.
It was a very
Like almost. You can talk about it as and like there is this technical is all about like perturbing how does a black hole function? Yeah.
You said? Oh, you're going.
Yeah. It's some real like thermodynamics.
It's a lot to process in one go.
No?
I think
I appreciate it.
It's better staying on site. There's I've seen air. Because it's the same.
You guys, yeah, I mean, you get a strong Scottish accent. It's impossible to stop.
I feel like I've seen that.
What do you mean this is on your back?
So I have a little bit like
It's a really
I think so. She's still kind of just like meant to be that glimpse out there in my head.
I've been here like
I will not be. That's a fun.
I did my undergrad.
Did you come to?
Oh, so this is to the computer.
Yeah, I
It's like USB power to both the webcam and the.
That's also what I'm wearing. Alright, they go to your Python.
It's really clutch, like in December.
I know you don't want it.
I said,
We're not. Well, no, I'm gonna just not.
Okay. Tyler, you ready? All right, welcome back, everybody. How's it going? Did you get your last beers? That's good. I'll take that as a yes. So now I'm going to be bringing up our final speaker of the evening. This is Tyler Gordon. He is a grad student of some amount of years in the University of Washington's astronomy department. What is that? 7? 7. So he's basically an expert. And Tyler is going to be talking to us about where the moon came from. Thank you, Tyler.
All right, so for the record, I've been here 7 years, but I haven't been studying this topic. So, this is an exam topic that was given to me, and so I had to learn a whole lot about it, and I thought I might as well use that knowledge to put together a public talk as well, so here I am. I'm also really happy to be up here just like presenting a talk and not hosting this whole thing. What I'm realizing tonight is that it's actually a lot easier to give a talk than it is to put this whole thing together, so I think we should give Megan another round of applause. All right, so yeah, I'm here tonight to try and answer the question, where did the moon come from? You might think like we would obviously have an answer to this question. We've been looking up at the moon for thousands and thousands of years, so I'm always going to be distracted by this cat, sorry. So we should have probably figured this out by now, but in actuality, we don't really know. So I'm starting out with the answer. I'm just going to tell you right off. We don't know where the moon came from. But of course, that's a little bit of an exaggeration. We know a lot about where the moon came from. We just don't know all of the details. So really what I should have titled my talk, it wouldn't have been quite as catchy, but I should have said something like, how we figured out kind of where the moon came from and what we still need to work out about the details. But this wouldn't fit on the poster, so I had to shorten it a little bit. All right, so I'm going to jump right into kind of an outline of my talk here. What I'm going to do is try to sort of lay out for you how we figured out what we do know about the origin of the moon. And I'm going to start by detailing some characteristics of the moon that need to be explained by an origin theory of some sort. And then I'm going to move on to talking about all of the different ways that you can form a moon. Some of these are ways that other moons in our solar system have been formed. Some of them are more theoretical. These are all ideas that have been forwarded for how our moon formed at some point. So I'm gonna run through those, and as I do that, I'm gonna talk about how well each of those formation mechanisms explains the observable traits and characteristics of the moon. And when I'm done with that, I'm gonna talk about what's still missing from even our most successful models, and what kinds of mysteries remain about the processes that formed the moon. All right, so to start out, I'm going to walk us through some of the characteristics of the moon that need an explanation. And just to kind of outline what's going on here, what you're going to find is that our moon is pretty weird compared to other moons in the solar system. It's very, very unique, which points to the fact that it was formed in probably a very different way than any other solar system moons. So the first thing I'm going to talk about is the mass of the moon. The gist of this is that the moon is really, really massive compared to other satellites in the solar system. It's not the most massive satellite in the solar system, but in terms of the ratio between its mass and the planet it orbits, the Earth, it is by far the most massive in relative terms. So I have a little plot here. This is one of, I'm only going to show 2 plots in this talk. And this is the easy one. The hard one comes later. So what I have on the x-axis, and do I have it? Okay. On the x-axis here, I have the mass of the planet. That's not super important. That's just to kind of spread everything out here so that all the planets land in a different spot on the x-axis. On the y-axis, I have the mass ratio, the moon's mass divided by the planet's mass. And what you can see right away is that for all of these gas giants, there's actually a lot of moons here, and it's hard to see because they're kind of all bunched up. But these all sit at almost 0. Most of these have masses relative to their planets of about 1 part in 10,000. So the planet is about 10,000 times more massive than the moon. But then you get over here to the Earth on the far left, and you see that the Earth's moon has about 1.2% the mass of the Earth. So it's like 3 orders of magnitude, two orders of magnitude. 2 to 3 orders of magnitude more massive relative to its planet than for any other planet in the solar system. So that's weird, and that needs and deserves an explanation. Next, I'm going to talk about angular momentum. And to talk about angular momentum, I'm actually going to have to go into just a little bit of detail about the tidal interaction that takes place between the Earth and the moon. But I've got some cool animations to make this a little bit simpler. So what I've drawn here is the Earth in blue and the moon in gray. And notice that they're both, they're not circles. They're kind of ovals. And that's to exaggerate the effect of tidal forces between these two bodies. So the moon pulls harder on the part of the Earth closer to it, and so that has the effect of stretching the Earth out into kind of an oval, and the same for the moon. Now, that deformation doesn't happen instantaneously. The materials in the Earth take time to kind of deform and stretch out and form that bulge. And that's gonna have an important effect here. So the Earth, what I'm showing you here with this arrow is the Earth's rotation. It's rotating counterclockwise in this view. The moon is also orbiting counterclockwise. The Earth rotates much, much faster than the moon orbits. We know from trivia that the moon orbits every 27.3, was it? Cool. I was going to say 28 days, but we have an exact answer from trivia, so I better stick with that. And the Earth rotates. Does everybody know how fast the Earth rotates? How many times per day does the Earth rotate? 0.98. I was going to say 1. I round to the nearest whole number. So what happens is that as the Earth rotates kind of underneath the moon, because that tidal bulge takes time to form and deform, it actually ends up kind of leading ahead of the moon. And then there's another gravitational interaction that happens. This is the actual tidal interaction, where that bulge, since it's ahead of the moon, it tends to pull the moon forward in its orbit in that direction, kind of accelerating the moon or adding momentum to the moon's orbit. At the same time, the moon is pulling that tidal bulge backwards because of its gravity and slowing the Earth's rotation. So what you have happening over time is the Earth losing angular momentum as it gives that angular momentum up to the moon, which is gaining angular momentum. And what happens, kind of weirdly enough, this is a little bit counterintuitive, but this is how orbital dynamics works. When you add energy and angular momentum to the orbit of an object, it doesn't just speed that object up in its orbit, it actually causes the semi-major axis of the orbit to increase. So the orbit widens and the moon moves outwards. So you've probably heard that the moon is receding from the Earth and moving away from the Earth. And it is, and this is why. It's because of this tidal interaction. But what we can do is we can kind of run this backwards in time, and we can figure out what would happen if you pulled the moon all the way back into where we think it was when it first formed. Kind of like a figure skater pulling in their arms, or like a kid on a rolly chair pulling in their arms and legs so they can spin around really, really fast. And when you track that backwards for the Earth, what you find is that the Earth originally would have been spinning around once every 5 hours instead of once every 24 hours. And you'll just kind of have to take my word for this, but that's really, really fast compared to what we see for other planets in the solar system as well. So the Earth started out when the moon was formed with a lot of angular momentum. So that's kind of our second fact that needs an explanation. Now I'm going to talk about some sort of more like chemical and structural traits of the moon and the Earth. So I'm going to talk about volatile element depletion. What do I mean when I say volatile elements? Well, I mean substances that vaporize at relatively low temperatures. So this is just a few examples, but this includes oxygen, nitrogen, hydrogen. What I have here is a picture of the Earth's atmosphere, which is made up of these volatile elements. It's mostly oxygen and nitrogen, and then, of course, that hydrogen can combine with oxygen to form water, which explains the clouds that you see here. So the Earth is full of volatiles. But what about the moon? Well, here's kind of the famous like Earthrise picture from the Apollo program. And what you can see right away is the moon is this beautiful blue marble, or the moon. That's not the moon. Earthrise. Earthrise, not moonrise. The Earth is this blue marble. It's covered in clouds. It's blue because of water. These are all volatiles that we can see when we look at it from space. But if you look at the moon in the foreground here, it's sort of a barren rock, right? It has none of these same volatiles that the Earth has. Of course, volatiles don't just exist on the surface of a world. In fact, we might not expect the surface of the moon to be covered in volatiles because the moon's really small. It doesn't have a lot of gravity. It has trouble holding on to, like, gases would tend to escape into space. But we can also look under the surface. And in fact, on the Earth, a lot of the volatiles that make up the volatile budget of the Earth exist in the mantle underneath the crust. Sometimes they make their way out. So what I have here is a picture of Mount St. Helens outgassing. So this is one of the ways that volatiles inside of the Earth can make their way out into the atmosphere. So we can look on the moon. We can try to figure out what kind of volatile content might be underneath the crust of the moon. We can do that by sampling rocks on the surface of the moon and looking at the volatile content of the minerals. We can do that for rocks that have been kind of excavated from deeper layers of the moon by impacts. And what we find is that we just cannot account for the amount of volatiles that we see on the Earth. So that's what we call volatile depletion. The moon has fewer of these kinds of volatile elements and substances than the Earth does. So that also needs to be explained. The moon is also depleted in iron. So here's sort of a schematic I have of the Earth and the moon. Most of the iron in these bodies, they're differentiated, meaning that the iron has all sort of fallen into the core of the object over time. And so most of the iron that you would see is in the core. We can measure the size of the cores of these objects using seismic experiments. We have those on the moon from the Apollo program. We have seismometers, and we can measure the way that seismic waves propagate through the moon and learn about the size of its core. And what we find is that its core is a lot smaller than the Earth's, which you might expect because the moon is a lot smaller than the Earth. But if we blow the moon up to the same size of the Earth and kind of put these on the same scale, the moon's core is about a quarter of the size of the Earth's core relative to the size of the moon. So that's what we call iron depletion. So that also has to be explained. Why does the moon have so much less iron than the Earth does? And the final characteristic of the moon that I want to talk about, and this one's going to be a little bit tough, I'm sorry, but we're going to walk through it slowly, is isotopic signatures. Okay, so what is an isotope? For example, I have lithium up here. I'm not going to talk about lithium at all after this. I'm going to talk mostly about oxygen, but oxygen has a lot more little, these are protons and neutrons. Oxygen has too many of them, and I didn't want to draw them all, so I used lithium because it has fewer. So lithium has two isotopes. Isotopes are two different versions of the same element that have different masses. So the most common isotope of lithium on the Earth is actually lithium-7, which has one more neutron than it has protons. It has 3 protons, 4 neutrons. I'm coloring the neutrons green here, just kind of arbitrarily. Lithium-6 has 3 protons and 3 neutrons, but they have the same electrons, which means that they kind of behave the same chemically. So this is what isotopes are. Okay, now let's stop talking about lithium and let's start talking about oxygen instead because it's much more important. So say we have a rock on the Earth, for instance, and this rock is full of oxygen. It's not full of like dissolved oxygen gas or anything like that, but oxygen makes up some of the minerals in this rock incorporate oxygen. And we can take samples of that rock and we can figure out how much of different oxygen isotopes exist inside of that rock. So what I have here is oxygen-16. I've got these little green dots for oxygen-16. That's the most common isotope of oxygen. but there's also a heavier version of oxygen with an extra neutron, that's oxygen 17, and an even heavier version, that's oxygen 18. And what we can do, ignore the math, I should have taken that out, but what we can do is we can define these two quantities. So delta 17 oxygen is the amount of the oxygen 17 isotope relative to some standard, and delta 18 oxygen is the same for oxygen 18. It's a measure of the amount of oxygen 18 that there is relative to some standard that we take. Usually we use a rock from the Earth as the standard. And the important thing to know here, and the kind of interesting thing, you can ask me about this afterwards if you want, I'm not going to explain it right now, we're just going to take it as a fact. This ratio between oxygen 18 and oxygen 17 is always the same for samples from the same planetary body. So any rock you get from the Earth will have the same ratio between oxygen 18 and oxygen 17. Any rock you get from Mars will have the same ratio, but it'll be different than what you see from the Earth. The same is true for samples that you take from asteroids. So it sort of uniquely identifies where a rock came from. And so what we can do is we can plot this ratio for different objects in the solar system. What we have here is, so this is delta 7. I said there were 2 plots. There's 3 plots, actually. The really hard one comes even later. This is still one of the easy ones. So this is delta 17 on the y-axis, delta 18 on the x-axis. Now, because these have the same ratio for samples from the same body, if you take a lot of samples from the same planetary body, they'll all line up along a line with the same slope. So this TFL stands for terrestrial fractionation line. So this is the line for the Earth. Above that is the line for Mars. These diamonds are all samples from Mars, so they line up right along the Mars line like we would expect. Down here, the HED is a class of meteorites that we think have broken off from the asteroid Vesta. They all line up along a line with the same slope. And then, if we take samples from the moon, what we find is that they sit exactly along the terrestrial fractionation line. So that's an interesting puzzle, because we would expect that different objects that come from different places in the solar system would have different fractionation lines, but the samples from the moon are almost exactly the same as Earth. And we can do this for different isotopes too. We don't only have oxygen, we have lots of other elements that we can do this kind of isotope game for. And what we find for all of them is that samples from the moon are exactly the same as samples from the Earth. They have the very same isotopic signatures. Or if there are any differences between them, those differences are explainable in terms of known processes that would have happened after the moon's formation. So this is a really important one, and we're going to come back to this a little bit later. Okay, so that's your overview. These are the characteristics of the moon that we need to explain in terms of a formation model. So now let's talk about some of the different mechanisms that we know can form moons in our own solar system, possibly in other solar systems. And as I do that, I'm going to talk about how well each mechanism explains the traits of the moon that I just outlined. Okay, so to start, I'm going to talk about an idea called fission. This goes all the way back to a guy named George Darwin, who first put this idea forth in 1872. George Darwin is, here's a little trivia fact, that is actually the son of Charles Darwin. Charles Darwin's son was an astronomer, and he thought about the moon a lot. So the fission idea is kind of well illustrated by this picture from a very, very old popular science book called Hutchinson's Splendor of the Heavens, which is a lovely name. The idea with fission is that you would have the Earth, so we're kind of moving top to bottom in this image. You would have an early Earth that is spinning really, really fast, and because it's spinning so fast, its equator kind of bulges out under the force of that rotation. And if you have some asymmetry in that equatorial bulge, it can just sort of like glob off of the Earth. It can fission off of the Earth like a cell splitting or something like that. Just under the force of that rotation, basically, it's like if you spin a pizza too fast or something and a piece of it just like pops right off because you spun it too fast. That's the idea here, that could happen with the Earth. And that piece that flies off the Earth will go out into orbit, and that'll form the moon. This was actually kind of the very most popular theory of the origin of the moon for a long time. It was so well accepted that it made it into textbooks, it made it into popular science books. Another sort of fun aspect of this idea that a lot of people have put forth is the idea that the space that the moon left behind could actually be the Pacific Basin. So this big depression in the Earth's crust, maybe that's where the moon was, and it got thrown off. There's a lot of things wrong with this. So this was before we understood like anything about plate tectonics. There's a lot really wrong with this idea, but to a lot of people it made a lot of sense that maybe the moon just sort of like popped out of the Pacific Ocean one day. So this, you're going to be kind of surprised when I start. I'm going to kind of grade this idea in terms of each of the characteristics that we talked about: angular momentum, mass, volatile depletion, iron depletion, and the isotopes. You're going to be a little bit surprised because that idea sounds so absurd, and I kind of put it forth like it was absurd, but actually it does very well when we kind of grade it against all of these metrics. So does it explain the angular momentum, the high angular momentum of the early Earth? I put a question mark here because not really. It requires a high angular momentum for this to work, but it doesn't give any explanation of why the Earth was spinning so fast in the first place. Does it explain the mass of the moon? Why the moon is so massive? Yeah. Why not? Who knows how much stuff could like pop off of the Earth? You can just kind of say, yeah, like it was a lot of mass, so the moon's big, whatever. Does it explain the volatile content of the moon? Not really. So the moon is deficient in volatiles compared to the Earth. That could happen because a high energy process can drive off those volatiles. This fission is not a high energy process, so when this mass kind of like blobs off or fissions off of the Earth, it should carry with it the same volatile content that the Earth had. So it doesn't really explain why the moon is depleted in volatiles. It does explain the low iron content of the moon because that stuff, that material that flew off of the Earth would be mostly from the crust and the mantle. It wouldn't include any of the core material. So you would expect it to have less iron than the Earth does. And it explains the identical isotopes because that material is literally coming from the Earth. So it would have exactly the same isotopic signature as the Earth does. So all in all, this doesn't do too badly. We get kind of 3 out of 5, or maybe 3.5 out of 5 if we count this question mark. It's not the worst theory in the world. It explains a lot of the characteristics that we measure on the moon. Also, at the time, nobody really knew that the moon was depleted in volatiles because we hadn't gone there in 1872. We didn't really have samples of the moon that we could like check in detail and see if they had like a lot of hydrogen in them or not. So, you know, not bad altogether. But let's move on. There's another idea. This is called capture. And this is the idea that the moon might have formed somewhere else in the solar system and been kind of caught by the Earth at some point. So this is our simple schematic of how that could happen. Here you have an object coming in, and it starts going into orbit around the Earth, and somehow it starts to lose energy and angular momentum, and that's how it gets captured. This is a more complicated model, so this is showing kind of a crazy trajectory that some object could take when it comes into orbit around the Earth and how it could get captured. This has actually, we know that this happens. We have other moons in the solar system that we think were formed by this mechanism. So Neptune's moon Triton, so this is Neptune, this is Triton up here, is thought to be captured from the Kuiper Belt. So it's an icy object that formed on the edges of the solar system and then got captured into orbit around Neptune at some point. It's also possible that Mars's moons, Phobos and Deimos, are captured asteroids. So this is something that we know that this can happen. Did this happen for the moon? Well, let's kind of investigate this a little bit. Okay, angular momentum is a problem because the moon-Earth system, like I mentioned, has a lot of angular momentum. If some object comes in with a lot of angular momentum, it's hard to stop that, to slow that angular momentum in order to capture it into orbit around the Earth. So the high angular momentum of the system sort of indicates that this capture mechanism would be difficult and unlikely to take place. The same is true with mass. A more massive object is harder to capture into orbit because it has more momentum, and you have to kind of arrest that momentum in order to get that object to come into orbit. So the high mass of the moon is inconsistent with this idea as well. What about volatiles? Well, this just depends on whether the original object formed with a lot of volatiles or not. If whatever object eventually was captured to become the moon was lacking in volatiles, then we would expect the moon to be depleted now as well. So that's kind of a question mark because it kicks the can a little bit. You'd still have to figure out, okay, where did this thing come from that it's volatile depleted? The same with iron. It just depends on where this object initially formed and what kind of material it formed out of. Isotopes, this is the real nail in the coffin for this one, in my opinion, because there's no reason to think that whatever object was captured by the Earth would just happen to have exactly the same isotopic signature as the Earth. In fact, there's a lot of reasons to think that it would not have the same isotopic signature as the Earth, because we know that objects from elsewhere in the solar system tend to have very different isotopic characteristics. All right, so our next idea is co-accretion. This one goes all the way back to 1755. I think I forgot to mention, but the previous one went back to like the 1600s or something like that. This is just to point out that these are old ideas that have been around for a really, really long time, and we're still kind of seriously thinking about some of these, which is kind of fun. So co-accretion is this idea due to Immanuel Kant, who most of us probably don't think of as an astronomer, but you know, he dabbled. This is a simulation of accretion happening. This is actually showing accretion around the sun, but we can pretend that this is a planet. So say this is a planet like Jupiter. It is accreting material from kind of the protosolar nebula, so all of this matter out in space around the sun in the early days of our solar system is being pulled gravitationally onto these bodies. If this is a planet, it would form its own kind of little accretion disk around it, and other smaller bodies could form out of that, just clumping together under the influence of gravity, mass coming together to form moons. So it's basically like forming a miniature solar system. That is how we think that the moons of Jupiter and Saturn formed, at least the most massive moons. So this is another thing that we know happens. So the question becomes, could this have happened for the moon? Could this explain where the moon came from? So let's get our little scorecard out again. What about angular momentum? It doesn't really explain the high angular momentum of the Earth-Moon system at all. There's no reason in this scenario for the moon to have a high initial spin, to be spinning at that like 5-hour rotational period. It doesn't really make any sense. What about the mass of the moon? This one's a real problem, and that's because simulations of this accretion process show that satellites formed in this method should have a very specific upper mass limit, and it's much, much less than 1.2% of the mass of the planet. You would not expect to be able to form a moon that large through co-accretion. And don't ask me exactly why. This just comes out of simulations, like big physics simulations and supercomputers that people do of this process. Now, volatile depletion. So you can see co-accretion's not doing great already. Like, it's already not going to pass this test. The volatile content of the moon is not explained in this scenario, and that's because if you're accreting the moon out of the same material that formed the Earth in this protosolar nebula, then you would expect the moon to kind of inherit the same volatile content as the Earth. And so the fact that it's depleted in volatiles is a little bit of a mystery if you're thinking of this co-accretion hypothesis. What about iron? It's the same deal as the volatiles. If the moon is accreting out of the same material as the Earth, then it should inherit the same composition, and so it should have the same percent iron content as the Earth does. And we know it doesn't, so this isn't explained either. Okay, finally co-accretion gets a good mark, and that's on the isotopes, because in this case, the fact that it's formed out of the same material is actually an asset, because we would expect the isotopic signatures to be the same. Okay, so co-accretion overall has done very, very poorly, 1 out of 5, 20%, failed the test. All right, so we clearly need another idea. None of these previous ideas have done particularly well. There's one or more observable traits of the moon that are just not explained by any of these formation models. Fortunately, somebody in 1975, so this is much, much later than all of the other hypotheses that we've dealt with. This is kind of a latecomer on the scene. Hartman and Davis came up with this giant impact hypothesis. And this basically, spoiler alert, but this is basically how we know that the moon was formed. But I'm gonna get into the details here, and I'm gonna tell you why there's still several sort of big mysteries about this. This model does not explain everything, but it explains a lot. So we've kind of this has been the main theory that we studied for quite a few years ever since it was proposed, because it does very clearly the best job. But this is just the idea, quite simply, as the picture indicates, that some object early on in the Earth's history just came in and smashed into the Earth, and it knocked a bunch of material off of the Earth into orbit, and that material later sort of coalesced into the moon. Maybe much, much later, and maybe very quickly. It kind of depends on the version of this model that you accept. Here's a better sort of schematic of this process. So often researchers call this object that ran into the proto-Earth Thea. So we can call the impactor Thea. I usually just call it the impactor. And this is the Earth, or sometimes you would call that the proto-Earth, because it wasn't really the Earth yet, because what ultimately is the Earth is some kind of mixture between these two objects. So it smashes in, there's this impact, it knocks a bunch of debris out into orbit around the Earth, and that debris later coalesces to form the moon. That's the basic outline. So how does this do? Angular momentum? Excellent, because that impactor can actually impart a lot of angular momentum to the Earth. It can increase the rotation of the Earth when that impact happens, so it would explain why the Earth was rotating so fast early in its history. Mass, it explains the mass of the moon. These kind of impact simulations, if you put it in a supercomputer and run it through, you can easily reproduce something as massive as the moon in this way. Volatile content, it explains the volatile depletion of the moon, because this is a really high energy process. So all that energy you're putting into the system heats everything up and would tend to vaporize these volatiles, and they would be, lost to space, and they would not recoalesce into the moon. It also explains the iron content, because in these simulations, most of the material that makes up the moon is kind of scooped up or thrown out from the outer layers of the Earth, from the mantle and the crust, and not the core. So you would expect whatever eventually coalesces into the moon to lack iron. Oh, darn. Okay. Isotopes are still a problem. And that is because this is a little bit of a funny detail, but it turns out to be really, really important. That's because in all of these simulations, a large part of the mass that makes up the moon actually comes not from the Earth, but from the impactor. So if the impactor has different isotope ratios to the Earth, then that should be reflected in the isotopic chemistry of the moon as well. So this is a big problem for the giant impact theory. It's the only problem we have, but it's a big one. But this theory is kind of successful enough in other ways that we've kind of focused a lot of attention on this and moved forward under the assumption that this is basically what happened, and we just need to work out this isotope problem. Okay, so this is the other plot. This is the hard plot that I was talking about. So I'm going to take some time to explain this one. This kind of illustrates the problem with isotopes. So what I'm showing here, well, what I'm showing, what Meyer et al. In 2014 are showing, along the x-axis is a measure of the amount of mixing of impactor material with Earth material that goes into the moon. So over here at 0, this is indicating that you have perfect mixing of material between the Earth and the impactor, so that the moon and the Earth would both be made up of sort of equal parts of these two, of material from these two objects. And as you go over here to the right, you get to the point where at 100, the moon is entirely made up of material from the impactor, and the Earth has no material from the impactor. And then along the y-axis, you have a measure of the difference in isotopic chemistry, specifically the oxygen isotopes between these two bodies. And so what this is showing, what this outline is showing, is sort of the allowed difference in isotopic chemistry between Thea, this impactor, and the Earth, as a function of the amount of mixing that happens. So what this is telling us is that if you have perfect mixing of impactor material between the Earth and the moon, then the impactor can have any isotopic chemistry and it's fine. Everything's good. We've explained it all. But if you go up to even 10%, like less mixing between the Earth material and the impactor material, then suddenly, in order for this to make sense, given what we know of the moon's isotope chemistry, you can only have a very small allowed range of difference in the oxygen isotopes between the impactor and the Earth. And as you move out even farther, as you get to like 50% mixing, this range gets really, really thin. So the Earth's oxygen isotope content is right here at 0. So this range starts to get really, really thin, where the impactor, in order for this to be reconciled with the isotopic chemistry that we observe for the moon, the impactor can only have a very, very specific isotopic ratio, and it has to be really, really close to what we observe for the Earth. This shading, don't worry about it too much, but it's sort of showing the allowed outcomes for different versions of the giant impactor model. So people have tried to come up with models of this giant impact that sit way over here on the left, where you get like more mixing. So this is one of the ways that people try to kind of fix this isotope problem. They come up with like really specific ways of colliding these two objects that create kind of maximal mixing between those two reservoirs of material in order to resolve this isotope crisis. So those models are over here on the left. Kind of the more, they call it like the canonical model. The sort of original version of this model is way over here on the right, where you end up with lots and lots of impactor material in the moon and not very much in the Earth. And that's where you really have a problem with the isotopes, because this range gets really, really thin. You have to have an impactor that has basically the same isotope chemistry as the Earth does. And we know from like looking at the isotopic chemistry of other objects in the solar system that there just aren't a lot of things out there that happen to have the same isotope ratios as the Earth does. So just to kind of summarize this, there's a number of ways that we can try and fix this isotope problem that we have with the giant impact model. One of them is by imagining that there's some kind of equilibration of isotopes post-impact. So maybe after the impact happens, when you have this disk of material that hasn't quite coalesced into the moon yet, maybe in that stage you can have everything kind of exchange isotopes and come to some kind of equilibrium. We don't really know how that would happen. Nobody has a good idea. It's theoretically very hard to figure out how that equilibration process could happen for a lot of reasons that I won't go into. You could have accretion of equilibrated material onto the Earth and the Moon after their formation. So maybe if a whole bunch of meteorites and asteroids come in and run into the Earth and the Moon and leave like a layer of material on top that all has the same isotopic chemistry, then maybe when we observe these things, we would see that they have similar isotopes, even if underneath they don't have similar isotopes. But the thing is, we can see underneath, and we know that they don't have identical isotopic chemistry underneath their crust. So this doesn't really work very well, but it's an idea people have had. Like I mentioned, we can imagine that this impactor has exactly the same isotopic signature as the Earth. There's no reason to believe that that would be the case, though. We don't know where such an impactor would come from. There are no asteroids that just happen to have the same isotope ratios as the Earth does. So where would that impactor have come from in the first place? We don't know. If we could find one, then maybe this idea would become a little bit more feasible. And then finally, we can tune these impact parameters in order to get a high degree of mixing between the Earth and the Moon. So this is the option that kind of the most attention has been focused on, trying to come up with different ways of simulating this impact that creates kind of maximal mixing of material. And that would explain how we could get something that looks like the Moon as well. So what I kind of want to leave you with is that this is still very much an area that's open to research. People are doing a lot of work on this. So we kind of we're in this place where we know sort of how the Moon formed. Probably something ran into the Earth and threw material off, and that formed the Moon. But the details of that process are very much a mystery to us, and there's a lot of reasons that we can't exactly figure out the details of how that process has happened. So I guess kind of what I want to leave you with here is that as you look up into the night sky, as you look up at the Moon, you're looking at something that is still, despite all of these years that people have been thinking about this question, despite all the research that has gone into this, you're looking at kind of a real-life scientific mystery every day when you look up at the Moon. We fundamentally do not know how it got there. Something crashed into something, but the details of that process are a total mystery to us. There's a lot of unsolved physics there. And finally, I'm gonna see if I can play this for you. This is a really recent simulation of an impact between the Earth and the Moon. The authors of this simulation claim that they've maybe sort of solved this problem just by doing a much, much higher resolution simulation than any that have been done before. So their idea is that maybe what's wrong with our simulations, why we fail to explain The isotope ratios of the moon is just that our simulations are too low resolution. So this one has a lot more particles and has a much higher time resolution than any that have been done before. I don't really know much about the simulation except that it's kind of a pretty picture. Okay, let's here. We gotta try to play this. I got this. This is a linked YouTube video, so it's a little bit tricky. I'm just gonna try to click on it. No, okay, it's pulling up YouTube. We'll see if this works. I don't think it's gonna work. Okay, so here's what you would see if you watch that. You would see, oh. Okay, well, it's basically just a pretty picture. Yeah. I'm gonna leave this up here. If it decides to play, we'll all enjoy it very much. Okay, you can all just watch that play. I just thought it was like a cool video to watch. But in the meantime, as we have that going in the background, as we let that load, I will happily take questions at this point. There we go. Okay, so this is a simulation that this group did. You saw that collision happen, and you see the stream of material that was flung out from the Earth. This is eventually going to coalesce into the moon. It's going to go through a little bit more tidal disruption before it does. But this is kind of what that collision process can look like. All right. Okay, are there any questions? Yeah. That's a really good question. I don't know exactly the timescale, but my understanding is that this is a matter of hours to days. So another thing that's remarkable about this particular simulation is that it suggests that the moon could have formed really, really quickly. Not over years or tens of years or hundreds of years, but literally in a matter of days. It would have taken much longer for that to kind of cool into like the moon as we know it today. But yeah, this simulation, this group is suggesting that maybe this process actually happened in, what is kind of cosmically the blink of the eye. Timescales that we just keep it going. We can keep it playing. And a timescale that like you as a human could watch if you were around back then, you would be very dead. The collision would be pretty bad. But if you survived it, you could just watch the moon form. Yeah.
How confident are they that the geology of the moon is pretty consistent around the moon?
Yeah. So the geology of the moon kind of happens much later, and that's because this is a high energy process. There's a lot of you're left with a moon that's very, very hot and molten. And the geology that we observe on the moon today is a result of that cooling process, and then of like later bombardment by meteorites over the history of the solar system.
But as far as the isotope ratio within...
Oh, I understand your question now. Yeah. So that is a little bit of a question. So we have samples that we think have come from the far side of the moon, from meteorite impacts and things like that. But it is a little bit of an open question. I think the fundamental problem is that the moon has not been like well sampled or evenly sampled, right? We have Apollo samples, and those are all from the near side of the moon. We have some meteorites from the far side of the moon. We don't know if we're talking about like volatile content or isotopes. We don't know if there's like heterogeneities. So if there's differences from spot to spot on the moon in how those isotopic signatures show up or how the volatile content shows up. We don't know for sure that there might not be like chunks of the moon that have a lot more isotopes or a lot more volatiles, but we also have no evidence that we do. All the samples we do have are consistent. So it would be a little bit of a surprise if there was like, if all the volatiles on the moon were hanging out in like one little spot. Yeah, you there in the middle. Actually, up front here first, yeah.
How unique are isotopic signatures? Like, how many overall are there? Like, could there be a chance of them, not necessarily in our solar system, of there being another one that matches Earth's?
Yeah, that's a good question. So I think maybe it'll help a little bit to get into why isotopic signatures vary across the solar system. And the reason for that is that in the protosolar nebula, so as the sun, when the sun was young and the planets had not yet formed and all of this material was kind of in an accretion disk around the sun, differences formed in the isotope ratios across that protosolar nebula. So heavier isotopes tend to fall inwards towards the sun, and lighter isotopes tend to end up further away from the sun in that disk. And so when these planets form in that disk, what happens is they lock in the isotope ratio at that point in the disk. So that's why Mars has a different isotopic signature than the Earth does, because it formed further out than the Earth, and so it has the isotopic signature that's characteristic of that distance from the sun in this nebula. So for something to have the same isotopic signature as the Earth does, that would imply that it formed basically in the same orbit as the Earth, which is dynamically sort of unlikely. It could happen. So that's where people say, okay, maybe this impactor was like hanging out in Earth's orbit at like one of these like gravitationally stable Lagrange points or something like that. That's kind of the idea there. So if you're talking about things from like other solar systems or something like that, first of all, I will say that there's no evidence whatsoever, and I would suggest that it's unlikely or even impossible that the moon could have come from another solar system for a variety of reasons. It would probably have way too much speed with respect to the solar system to ever get pulled into Earth's orbit or anything like that. But if it did come from, that point in its own protosolar nebula where the isotope chemistry happened to be, the same as the Earth, then you could have a similar isotopic signatures. But it's not common for things to travel solar system to solar system, and if it did, it would just shoot straight through, and it would never get pulled into the Earth's orbit or anything like that. Yeah, last question.
What depth are you guys looking at with the lunar, like the rocks on the lunar surface?
Yeah. So not very deep. This is another problem, is that we have samples from the surface of the moon. Those include samples that are, sitting at the very surface of the moon, but also rocks that have been excavated by impacts that come from a little bit deeper in the crust. But we can't go to the moon and drill deep into the interior and take a sample out. On the Earth, we also have the benefit of volcanoes that kind of churn material up, and we can... I'm not a geologist, so I don't know all the details, but there are ways of sampling material that we know comes from deeper in the Earth. There's also cases where you get material, like certain rocks that formed really, really deep at the bottom of the crust or in the mantle, that end up on the surface through various means, and so you can sample those and say, okay, what we're getting here we know is from like a certain depth. So on the moon, of course, we can't go to the moon and like sample a volcano on the moon because there are no volcanoes on the moon. We can't drill way down into the mantle and sample that. Some of the similar sort of geological principles are in place, though. So you can find places on the moon where we have reason to believe that chunk of rock or that portion of the moon represents more accurately what you would find in the mantle of the moon because it's solidified out later, for instance. This is something that I don't know a lot about, but geologists who study this sort of thing, or planetary scientists, are able to get an idea of what's in the interior of the moon from these rocks. But it is a really good question because it's hard to know exactly what's going on like deep in the moon where we can't look. So maybe there's more volatiles hiding out there. Maybe there's a gradient in isotopic chemistry that changes as you go from the surface down into the depths of the moon that would kind of help to explain the discrepancy. So that's an open question as well. And I think we got to cut it loose there. You should come up and ask me a question afterwards because I saw you had your hand and I kind of skipped you. But yeah, we're gonna call it good there. Thank you so much, everybody.
All right, thank you, Tyler. Let's give one more round of applause for both of our speakers tonight. All right, the next Astro on Tap is going to be on November 30th. That's the last Wednesday of the month. And please note, we are switching to an earlier time. We're going to go to 7 p.m. because of daylight savings time. So we're starting an hour earlier than we did tonight. Thank you all so much. Oh, and if you won trivia, come up and see Sam to get your prize. Have a wonderful night and get home safe.
Hehehehe